Welcome back to G Fun Facts Online. Today we are doing a deep dive into the invisible war happening right now in the fiber optic cables beneath your feet. We are going to talk about the end of secrets and the physics-based shield that is being engineered to save them. We are talking about quantum key distribution on photonic chips. If you follow technology, you have probably heard the term quantum computing thrown around as the next big thing. But there is a dark side to this revolution, a threat known in the intelligence community as Harvest Now, Decrypt Later, or HNDL. This is not science fiction. It is happening right now. Adversaries and state actors are currently scraping petabytes of encrypted traffic, your financial records, diplomatic cables, military secrets, and intellectual property. They cannot read it yet because it is locked behind RSA and ECC encryption, the mathematical locks that secure the internet. But they are storing it in massive data centers, waiting for the day a cryptographically relevant quantum computer comes online. When that happens, perhaps in the early 2030s, those mathematical locks will shatter in seconds, and the secrets of the past decade will be laid bare. This is the timeline we are living in. But there is a response. A revolution is taking place not in software but in hardware, migrating quantum security from the size of a refrigerator to the size of a fingernail. This is the story of how we are using the laws of physics to build an unbreakable internet. Let's start with the physics, because to understand why a chip no larger than a grain of rice can protect a nation, you have to understand the fundamental rules of reality it exploits. Classical cryptography, the kind we use today, relies on complexity. It bets that a computer is too slow to do the math required to break the code. Quantum cryptography, specifically quantum key distribution or QKD, relies on the Heisenberg Uncertainty Principle. In our everyday classical world, you can measure a tennis ball's position and speed without disturbing it. But in the quantum world, that is impossible. The act of measurement fundamentally alters the state of the particle. This is the core mechanism of the quantum sentinel. Imagine Alice wants to send a secret key to Bob. She encodes this key into the quantum states of single photons, particles of light. She might use the polarization of the photon, horizontal versus vertical, or the time it arrives. If an eavesdropper, let's call her Eve, tries to intercept these photons to read the key, she must measure them. Due to the laws of quantum mechanics, her measurement inevitably disturbs the photons, introducing errors into the stream. It is like trying to read a message written on a soap bubble. The moment you touch it, it pops or changes shape. Alice and Bob, by comparing a small subset of their data, can detect these errors. If the error rate is too high, they know Eve is listening. They discard the key and try again. This guarantees that if a key is successfully shared, no one else has a copy. This is backed by the No-Cloning Theorem, which states you cannot create a perfect copy of an unknown quantum state. Eve cannot photocopy the photon and pass the original to Bob. She leaves her fingerprints on the data stream simply by looking at it. Now, within this framework, there are two main protocols that engineers are hard-coding into chips today. The first is decoy state BB84, proposed in 1984. This is the workhorse of the industry. In modern chips, this is often implemented using time bin encoding because polarization gets scrambled easily in long optical fibers. A photon is passed through an interferometer on the chip, taking either a short path representing a 0 or a long path representing a 1. The second protocol is the E91 entanglement protocol, proposed by Arthur Eckert. This is the holy grail. Instead of Alice sending a photon to Bob, a source generates a pair of entangled photons. These twin particles share a spooky connection where measuring one instantly determines the state of the other, no matter the distance. The security here is guaranteed by the violation of Bell's inequalities, a statistical test that proves the correlations are truly quantum. This allows for device-independent security, meaning even if the chip manufacturer was malicious, the protocol would detect it. So, how do we take these tabletop physics experiments and put them into the real world? For decades, QKD systems were bulky optical tables filled with mirrors and lasers costing over $100,000 per link. The breakthrough has been the move to photonic integrated circuits, or PICs. Just as electronic microchips replaced rooms full of vacuum tubes, PICs print optical components directly onto a wafer. This miniaturization reduces cost, size, weight, and power, a metric known as CSWAP. But building these chips is a battle of materials. There are three main contenders. First, we have Silicon Photonics. Silicon is the giant of the industry because we can use the same massive foundries that build computer chips. It is incredibly cheap and scalable. However, silicon cannot generate light. It has an indirect bandgap, so it acts as the passive plumbing, holding the waveguides and splitters. Second, we have indium phosphide. This is the active powerhouse. Unlike silicon, it can emit light, meaning it can hold the laser, modulators, and amplifiers on a single chip. But it is more expensive and brittle. Third is the rising star, lithium niobate, specifically thin-film lithium niobate. It offers superior electro-optic properties, meaning it can change its refractive index instantly when a voltage is applied, allowing for ultra-fast encoding of keys. Let's take a fantastic voyage inside a typical 2026-era QKD transmitter chip to see how these work together. It starts at the source, where an indium phosphide laser fires a continuous beam of light at 1550 nanometers, the standard telecom wavelength. This beam hits the pulse carver, a Mach-Zehnder modulator that slices the beam into faint pulses running at speeds of 2.5 GHz or higher. Next, it goes through the attenuator. This is crucial. It dims the pulses until they contain, on average, less than 1 photon per pulse. If a pulse has 2 photons, Eve can steal one and let the other pass, a vulnerability known as a photon number splitting attack. Finally, the photon reaches the encoder, the brain of the chip. A complex nest of interferometers splits the photon into different time bins, or rotates its phase, using heaters or electrodes to encode the 0 or 1. Then, a grating coupler shoots the photon out of the chip and into the fiber network. The last 18 months, from 2024 to 2026, have seen this technology transition from a lab curiosity to a commercial necessity. Several landmark events have defined this period. In March 2025, Toshiba and KDDI research shattered a major barrier. For years, QKD required a dark fiber, a dedicated cable just for the quantum signal, which was prohibitively expensive. Toshiba demonstrated multiplexing, sending quantum signals alongside massive 30 terabits per second data streams on a single fiber over 80 kilometers. They did this by assigning the fragile quantum keys to the C-band, where fiber loss is lowest, and pushing the noisy classical data to the O-band. This spectral coexistence means telecom operators can upgrade existing networks just by plugging in new transceiver chips. Then in June 2025, we saw the launch of the Orange Quantum Defender. Orange Business and Toshiba launched the first commercially available quantum-safe network in Paris, serving the La Défense business district. This system uses a hybrid architecture, combining physics-based QKD for the core network with math-based post-quantum cryptography for the last mile. This defense-in-depth strategy is becoming the industry standard. Another massive shift occurred in early 2025 with the merger of IonQ and ID Quantique. IonQ, a leader in quantum computing, acquired ID Quantique, the Swiss pioneer of quantum networking. This signals the convergence of computing and communication. It is not enough to build a quantum computer. You must be able to network them to build the quantum internet. And we cannot ignore the miniaturization breakthrough by Ketz Quantum Security in April 2025. Using a monolithic indium phosphide platform, they packaged a full QKD system into a form factor small enough to fit inside standard consumer electronics, eliminating the need for complex active alignment. So who is buying this? Why are billions flowing into this sector? The banking sector is the first mover. A 2026 report by Citi Global Perspectives estimated the financial sector faces a $3 trillion risk from a single-day quantum attack. Giants like JP Chase and HSBC moved from piloting to deployment by 2025, securing high-value settlement systems. The massive back-end pipes where trillions move daily. Critical infrastructure is next. In October 2025, the U.S. Air Force awarded a contract to Quinect to deploy a metro-scale entanglement-based network to secure drone feeds and command links. This directly addresses the harvest now, decrypt later threat. If you do not have the key now, you can never decrypt the message, no matter how powerful computers become in the future. Even space is being conquered. Ground-based QKD is limited by fiber loss to about 150 kilometers. To span oceans, we need satellites. Following their acquisition of Capella Space, IonQ announced plans for a space-based QKD network where satellites act as trusted couriers, beaming photons between New York and London. However, challenges remain. The biggest is the trusted node problem. Currently, to go long distances, you need repeaters, but you cannot amplify a quantum signal without destroying it. Current networks use secure buildings to decrypt and re-encrypt the signal, which is a security risk. The solution lies in chip-based quantum repeaters, which require quantum memory to hold a photon in a crystal lattice. Companies like MEMQ and Connect are racing to perfect this. Another hurdle is packaging cost. Getting a single photon from a 9-micron fiber core into a 0.4-micron silicon waveguide is an engineering nightmare. Packaging accounts for 80% of the device cost, driving the trend toward co-packaging lasers and electronics on a single substrate. Finally, there is the debate between NIST standards and QKD. In August 2025, NIST finalized the post-quantum cryptography standards. Some argued this software fix was enough, but the industry has settled on a hybrid consensus. Software is for the masses. QKD is for the critical core. As we conclude, it is clear we are witnessing the dawn of the photon age. We are moving from security based on complexity, hoping the math is hard enough, to security based on physics, knowing the universe prohibits the theft. The chips being fabricated today are the first bricks of the quantum internet. As we look toward 2030, the question is no longer will quantum cryptography work, but rather is your network ready for the light? Thanks for listening to G Fun Facts Online.